Our second video is on angular displacement, the natural but uncomfortable, but hopefully it will be comfortable radian, and a rotating rat. So what I want to use for this example is a rat. I'm going to take, let's say, Lola, and she's been training for this race. There's a circular track, and she runs and she runs and she runs all the way around the track, but we're going to focus on the section from A when she starts to B, and we're going to look at her motion then. Thank you, Lola. So our definition of a circle is that all the points here are separated or the same distance away r from the axis of rotation or the origin. So this is our axis of rotation, and we're imagining it's coming out of the page as the rat goes around. And as the rat goes around the circle, it's traveling length s, or arc length s, from A to B, and it sweeps out this angle. So I want to give you guys, and I've given you the definition of the radian before, but we're going to hit on it again for this unit. The angle, or the angle of rotation, or angular displacement, you'll see it in any of those forms, is S over R. Now, if we're using radians, this theta is unitless because it's a ratio of two lengths, the length of the arc length and the length of the radius. So we should be able to then translate between degrees and radians, but I hope that you guys become comfortable using the radian because it makes all of your calculations and thinking about rotating objects much simpler. But if you do want to translate between the two, we know that 360 degrees is equivalent to traveling 2 pi, or sweeping out 2 pi radians, so we could set up a proportion. If I want to know how many radians are in 60 degrees, then I could say 60 degrees over x radians is equal to 360 degrees over 2 pi radians, cross multiply, solve for x, and x is about 1 radian. Be mindful on your calculators to switch from radians to degrees depending on what you're solving for and what unit you're using in any given problem. Now, I want to make the case to you guys, and I'll make the case over several videos, that rotational motion is so similar to linear motion. So if you are comfortable using linear kinematics in linear dynamics, like Newton's second law, then you should be comfortable with rotation as well. So in this scenario, I have 3 rats now, and they start off here, here, and here, and then go off to B1, B2, B3. All at the same time. Or maybe we could think of this better as a turntable viewed from above, and I've got 3 rats on it. They're still, but the turntable moves, and so they all hit these 3 points at the same time. We have the same angular displacement, but different arc length. So S3 is longer than S1, but the angular displacement is equivalent for all 3 motions. So in trying to relate the angular motion to linear motion, we want to get an expression for the s's. Well, we've already gotten that before, and we could say that the angular displacement in radians is S1 over R1, and it follows that with any given path, S3 over R3 would be the same radian. So in solving for the linear displacement, S, or this might be seen as x or y, whatever variable you want to call it, for linear displacement, it's equal to r times your angle in radians. More to come. Stay tuned.